Good day, Justin Milrocks on College Physics here. We're going to be looking at keeping things rolling. In a sense here, we want to start looking at some more rotational characteristics, and in this segment we'll be looking at translation of rotation. So we want to be able to understand not just something spinning around, but something that is spinning and translating that rotational motion into a linear motion. So we got a little cylinder here, circular cylinder, and what I can do is I can rotate it, but have it roll along something. That's what circular objects like to do, like when they're on the ground or going down inclines, all sorts of cool stuff. But ultimately, I want to look at this rotational characteristic and its connection with a linear type of motion. So I can take this, and I'm going to go ahead and rotate it one full rotation. So here we go. There we go. That's about one full rotation. I got a little meter stick, that's really centimeters here, that tells me it just rotated about 48 centimeters. Yeah, really close to exactly 48 centimeters. So what we want to be able to do is correlate that translation of rotation in a linear motion with the actual rotation itself. So how are we going to do that? We need to be able to gauge what the ultimate equivalence is between one full rotation and how much it moves forward. So we took this object, not too big, and it moved forward by 48 centimeters. Good deal. What happens if we take a different object, like this wheel here, and rotate it one full rotation? I'm going to start it way here at this end, and try not to knock anything over. It's gone around half. Is it going to make it? Not quite. A little bit more than this whole plank. That's a lot more than 48 centimeters, right? Why did this one, under one full rotation, move forward by so much more than this one? Well, it has to do with the radius, right? This one has a much smaller radius. So what we want to think about here is how much does a rotating object move forward over one rotation? How can we get that? So ultimately, again, it's connected with the radius, which is connected with the circumference. When something rotates, it translates that rotation into linear motion. Every time that it goes around, it lays out its circumference on the surface. So I spin this around, and it just advanced itself forward by a distance equivalent to the circumference of this. And the circumference of this cylinder here was a lot less than the circumference of that wheel. Thus, it doesn't move forward as much as the wheel under one full rotation. So, ultimately, this is what we want to look at. Translation of rotation into linear motion. So I'm going to go ahead and move this out of the way. Note that if an object that is rotating is contact the surface, and does not slip or slide across that surface, its rotation will produce a linear motion across the surface. every one rotation, the object will move forward by its circumference. Every full rotation, the object will move forward by its, will move forward by a distance. Equal to its circumference. So what we want to be able to do is utilize this and figure out the explicit connections not just between angular displacements and linear displacements, but angular velocities, angular accelerations, and linear accelerations for an object that is allowed to fully translate its rotation into linear motion. So that's what we want to do, and that's what we're going to do. So, here's a question for you. What happens if a circular object, excuse me, only rotates through half of a rotation? How much does it move forward? That's right, half of its circumference. What if it only rotates through a quarter of a rotation? It moves through a quarter its circumference, an eighth of its rotation, an eighth of its circumference. It's 1-to-1 in terms of that, right? So, one full rotation goes to 2 pi r linearly, as far as the distance it moves forward. So one full rotation, there's the circumference of a circle, 2 pi r, and that's how much it moves forward linearly. One half a rotation goes to 2 pi r divided by 2, right? Which was just going to be equal to pi times r. A quarter of a rotation, well, that's going to go to pi over 2 times r. And we could keep on going with this. What I want to really make the connection with here is it all depends on the radius, linearly, and it depends on this quantity here. Well, note that 2 pi radians, what is that? That's the angular measurement of one full rotation. 1 revolution, we'll say. Pi radians is a half of a revolution. Pi over 2 radians is a quarter of a revolution. Hey, these are really angles here. Angles in terms of radians, right? 2 pi times r. 2 pi radians times the radius is how much an object will move forward and undergoing one full rotation. So what happens if we just want to be able to start talking about any amount of a rotation? Well, we can consider sectors of a circle. And this will answer a couple questions for us. Take a circle here. Too bad of a circle. So that has some radius r here. That's good. And what we're going to do is say that this object rotates by some amount. By some amount, delta theta right there. That's how much it rotates. Doesn't matter which way it rotates by some delta theta. How much does it move forward? Well, it moves forward by this amount, right? What is that amount right there? Well, that's known as arc length. goes all the way around, delta theta is 2 pi radians, and the arc length is equal to the circumference. Goes halfway around, well, delta theta is equal to pi radians, and it moves forward by half of its circumference. Goes through quarter, moves through an angle of pi over 2 radians, and moves forward by quarter of its circumference. And so on and so on and so on. So what can we do with this? Well, we can go back and think about the connection between r, delta theta, and the arc length. So what do we have? Arc length is how much it moves forward, and that's equivalent to the radius multiplied by delta theta, or the angle under consideration, in radians. Must be in radians. This is why radians is the SI unit for rotation, because of this connection right here. As long as delta theta is in radians, we have a direct correspondence between the radius of the object and arc length for a given angle. And that is explicitly why we go ahead and use radians, because of that one-to-one connection. Let's think about a couple things here. Delta theta is in radians, right? Well, r, what's r measured in? It's a unit of distance. Let's say that it's measured in meters, SI units. What's s measured in? Well, that's a distance too. Let's say that that's an SI unit, it's meters. If we go ahead and we say, well, delta theta is equal to the arc length, s, divided by r, what do we have for the units of delta theta? Well, we just said delta theta has to be in radians, but this is going to be meters divided by meters. Distance divided by distance. That's actually unitless. There's no units. We call it radians just to note that how we are ultimately corresponding a measurement for some angle. But truly, it's a unitless quantity. Degrees, revolutions, radians, those are all unitless. We say it's an SI unit because of this connection between arc length and radius, but truly speaking, it is a unitless quantity itself. It's just the ratio of two distances. Two specific distances, yes, but two distances nonetheless. So, that's pretty interesting there, is it not? It's really a unitless quantity. But, that's that. Here's another thing that I like to kind of pull out here is, well, where does this pi come from anyway, right? Got 1 full revolution, 2 pi radians, 2 pi radians in 1 full revolution. So what is pi? Something we get at the bakery? Maybe. But we're talking about the mathematical pi here. So what do we have? Well, we have that circumference is equal to 2 pi times r, right? This is the connection between radius and circumference here. Well, what happens if we want to solve this out for pi? Pi is equal to circumference divided by 2 times the radius, which is circumference divided by diameter. That's what pi is. Pi is just a ratio. It is a ratio for the circumference of a circle to the diameter of that circle. And it is a constant value no matter what circle you're talking about. The ratio of a circle's circumference to its diameter is the definition of pi. That's where pi comes from. So that's kind of a little side note there, but some interest, I think. At any rate, we've got ourselves this, the connection between arc length, which is now equivalent to the distance that a translating object moves forward, corresponding to its radius and angle and your displacement of that object. So, let's write this out. From S equals R delta theta, we can write for translation, delta x is equal to r delta theta, where delta x is the linear displacement of the object in terms of its angular displacement, if it is rolling without slipping or sliding, wholly translating its rotation into linear motion. So delta x is the linear distance, object with a radius of r, the linear distance, and object with a radius of r, distance that an object, So the distance that an object with a radius of r will move forward by upon rotating through an angle, delta theta. In radians, if it wholly translates its rotation. Throw that on up there. So delta x is the linear distance that an object with a radius of r will move forward by upon rotating through an angle delta theta in radians if it wholly translates its rotation ultimately into linear motion. No slipping, no sliding. So this is what we've got. Delta x is equal to r delta theta. Well, what else can we get from that? That's just the correspondence between angular displacement and linear displacement for translation. Well, what happens if we divide both sides by delta t? Delta x divided by delta t is equal to r delta theta divided by delta t. What is this? That's average velocity, right? Delta x over delta t. What's this? That's average angular velocity. So we can write this as v average is equal to r omega average. Ooh, that's nice. This gives us the linear velocity in terms of the angular velocity and the radius of the object. Fantastic. What else could we do with this? Well, we can also think about this not in terms of deltas, but in terms of infinitesimal displacements and such, and start taking derivatives. If r is equal to a constant, that is, if the radius is not varying with respect to time, we can write that dx by dt is equal to r d theta by dt, which gives us the instantaneous velocity, v, being equal to r multiplied by the instantaneous velocity, omega. This is nice to be able to write out. If we know how fast it's rotating, and we know that it's translating its rotation, we know how fast it's moving forward. It depends though. It depends on its radius. The larger the radius, the more it's going to move forward for a particular angular rate. Likewise, we've got, and if we can do this all for velocity, we should be able to do it for acceleration too. We'll just write it out. Average acceleration can be written as r times alpha average, or we can write that the acceleration, linear acceleration, is r times alpha. So, go ahead and write these down. Think about a couple things here. Erase this one. angular displacement to linear displacement. Delta x is equal to r delta theta. Angular velocity to linear velocity. V is equal to r omega. And then angular acceleration to linear acceleration alpha, A is equal to r times alpha. So think about a couple of things here. What are the units of linear displacement, delta x? Sorry, SI units would just be meters. Well, before measuring the radius in SI units, that's just some amount of meters too, so distance. Which means that, well, radius, distance times the angle has to be just meters. Well, we call this still meters times radians. And again, radians is sort of, I think of it as a phantom unit. Sometimes it belongs, sometimes it doesn't. Depends on whether you're talking about a linear quantity or an angular quantity. It doesn't belong in linear quantities. So when we quantify delta x, v, or a, they're just going back to meters. Meters per second squared, where the radians phases out. If we're talking about angular quantities, well, if we solve this out for delta theta, we'd have that it is delta x over r, or omega is v over r, or alpha is a over r, where those all end up being unitless quantities. But since we're talking about angular quantities, radians phases in, and we call them radians for the angular quantities. So something you kind of got to get a little bit used to. But that's just a part of a rotation, a little bit more dynamic than just linear motion. One more thing we can look at regarding this, and that is just whether we could have extracted this to begin with. Let's make sure that this all makes sense. Let's consider constant angular acceleration. Consider constant alpha. We've got equation of motion for constant angular acceleration, We've got the delta theta is equal to 1/2 alpha t squared plus omega I times t, and omega final is equal to alpha t plus omega initial. Well, we've also got that A is equal to R times alpha. If alpha is a constant and R is a constant, we'll keep an R constant here. A is also equal to a constant. And we can write out equation of motion for constant linear acceleration, where we have delta x is equal to 1/2 a t squared plus vi times t, or v final is equal to a t plus v initial. Again, they have sort of the same form, right? Well, what else do we have? We've got ourselves the translation quantities. Which are ultimately delta x is equal to r delta theta, v is equal to r omega, a is equal to r alpha. What happens if I go ahead, this is delta x, sorry, I said delta x, and I put delta r. What happens if I put in these for delta x, v, and a over there? So I'm going to take these, and I'm going to substitute in those values for the delta x, a, and the v's. So let's take this first one. Delta x, well, delta x is equal to r delta theta, which is equal to 1/2 times a is equal to r alpha times t squared, plus v sub I, well, that's going to be r times omega sub I, times t. All right, what do we get out of this here? Well, look at every term has a common factor of r in it. R. You can factor it out, divide it out, it goes away. And what are we left with? Delta theta is equal to 1/2 alpha t squared plus omega I times t. Well, that's this expression here. This is just to show the validity of this all, the connection between them. Yeah, that's how it all works out. We can retrieve the angular counterparts for constant angular acceleration regarding looking at constant linear acceleration through, again, the translational quantities. So now we're going to be bouncing back and forth between angular and linear. Something's rolling, moving forward, it moves forward a certain distance. How fast is it going? How many rotations did it roll through? What's its angular velocity? All sorts of connections, lots of different quantities, but they're connected by the radius of the object under consideration. If you know the radius of the object, it's all just utilizing the same sets of expressions that we've used before. So at that, we should go ahead and do a little problem involving this, shall we? We shall. Be right back. All right, so here we go. Here's the problem. Okay, so we've got ourselves a wheel that has a radius of 0.35 meters, and it is initially rotating at a rate of 50 radians per second. It's across the level ground, and it is wholly translating its rotation into linear motion. This wheel is going to be slowing down as time proceeds, and over a distance of 20 meters, it's going to come to a stop. And we are under the pretense here of a constant angular acceleration. So, we got some questions regarding this, right? We want to know, what is the angular acceleration? What's the counterpart of that? What's the linear counterpart of that? Linear acceleration. Translational acceleration, we could call it. What amount of time does it take to stop? And then we'll kind of go on from there. So, these types of problems that involve a mixture of rotational and linear quantities require some attention. My suggestion is to make a little table, keep the quantities separated, angular versus linear, and you can always bounce back and forth between them if you know what the radius is. So we can start off with this, right? Angular. We know that the initial angular velocity is equal to 50 radians per second. And we've got some final angular velocity. Well, that has to be 0 if it's stopped. It's not rolling anymore, so that one's pretty easy. What else do we have? Well, we've got a delta theta, we've got an alpha, and we've got a t. So over on this side, just considering angular quantities, we only know 2 things. We need to know 3 to solve for either of the other 2. So just knowing 2 things doesn't do us anything. So we've got over here some linear quantities, and we've got some v initial, we've got some v final, which we know is 0. We've got some delta x, which we're told is 20 meters here, and we've got some a and some t. Well, over here, we only know 2 of the 5 things, so by themselves, that doesn't do us anything. We want to know first, what is the angular acceleration? So this is what we want to figure out first, this. So it would be nice if we just worked with angular quantities right now, right? So what can we do? Well, we can figure out what the angular displacement is based upon knowing what the linear displacement is. Because between the angular and linear, we have delta x is equal to r delta theta, v is equal to r omega, and a is equal to r alpha. There's the translation. Equations of translation. So we just start with that. Let us just go ahead and figure out what this delta theta is here. Then we know 3 of the 5 things, and we can figure out what is alpha. Once we know alpha, getting A is easy. And then we can figure out T2. Boom, boom, boom. Right down the line. So let's just go ahead and figure out what delta theta is. Well, we've got ourselves that delta x is equal to r delta theta, which gives us the ability to say that delta theta is equal to delta x divided by r, which is then 20 meters divided by the radius of 0.35 meters, giving us that delta theta is equal to 57.143, we'll call it. 57.143. Well, here it says it's unitless, meters divided by meters, but this is radians here. Because if we're using this, delta theta has to be in radians, so throw in some radians there. Radians phases in because it belongs on an angular quantity. So we know this, 57.143 radians. So now we can use those three quantities in the equation of motion for constant angular acceleration to go ahead and figure out what is alpha. So we think about the equation of motion for constant angular acceleration, knowing what both alpha, omega final, and omega initial are, delta theta, omega final, and omega initial, trying to figure out what alpha is. We've got this. Omega final squared equals omega initial squared plus 2 alpha delta theta. We want to solve that out for alpha. We know omega initial, omega final, delta theta. Solve this out for alpha. Alpha is equal to omega final squared minus omega initial squared divided by 2 delta theta, which gives us then, omega final is equal to 0. Omega initial was equal to 50 radians per second. That quantity is now squared, divided by 2 times delta theta, which is 57.143 radians. What do we get? We get ourselves an alpha. That should be positive or negative before calculating anything. Object's slowing down, right? We're treating all the other quantities positive, angular displacements and angular velocities. So angular acceleration better be negative, slowing down its rotational rate. And it turns out to be negative 21.875. Negative 21.875 radians per second squared. Excuse me. So there is our angular acceleration, part A. So at that, we can move over to part B. Part B asks, hey, what is the linear acceleration or translational acceleration that correlates with this object's motion? Now that's going to be really easy to get because all we got to do is look to the equation of translation because we already know what the angular acceleration is. A is equal to R alpha, which is equal to 0.35 meters multiplied by negative 21.875 radians per second squared. And we get ourselves negative 7.656. Negative 7.656. What do we want to call this? Do we want to call it meter radians per second squared? Radians doesn't belong in a linear type of quantity. Radians phases out. Doesn't belong in this. It's really unitless. It just disappears. So we just call it meters per second squared, as we should. So there's the linear acceleration of this object. It slows down at a rate of 7.656 meters per second. Every second that goes by, over a 20-meter distance, it comes to a stop. Fantastic. What amount of time does it take to stop? To stop. Well, at this point, we have a couple different ways that we could go with this, but since we know so much about the angular quantities at this point, let's go ahead and stick with those. So we know that the angular acceleration was a negative 21.875 radians per second squared. So that's good. So let's just go ahead and figure out t from that. Because we've got that omega final is equal to alpha t plus omega initial. We can solve this out for t being equal to omega final minus omega initial divided by alpha, which is 0 minus quantity of 50 meters per, not meters, sorry, radians per second divided by negative 21.875. radians per second squared. Radians per second divided by radians per second squared will give us seconds, as it should. The negative signs cancel out as better. And we've got 50 divided by 21.875. We've got about 2.2857. 2.2857 seconds is how long it takes this object to stop. There we go. All right, there's the A, B, C. Now I want to move on to a D, E, and F, which are asking some different things about this system now. So, part D says, how long does it take this object to obtain a speed of 10 meters per second? Look at the units. That is linear. So we want to know how long it takes to achieve a linear velocity v of 10 meters per second. Well, that kind of changes some things, right? We don't want to say that v final is 0 anymore, or that delta x is 20 meters, because after I move 20 meters, it's at a stop. It should move 20 meters and be moving 10 meters per second, right? So we got to kind of revamp some things here. I'm going to throw this on up here, and I am going to go ahead and erase some things. Now there's some things that stay constant, some things that do not. The angular acceleration, that's a constant of the system. This angular displacement goes with it going all the way 20 meters. Well, it's not moving 20 meters if it has a non-zero final velocity. So that is not 0, and that is not 0. The initial angular speed, that is a constant of the system from where we're starting anyway. So that remains the same. So let's go back over and note that we want to know something about it going 10 meters per second. We could deal with linear quantities, angular quantities, and switch back and forth. Not going to bother. We're going to go ahead and just use some linear quantities here. So we know that the final linear velocity that we want is 10 meters per second. All right. And we also know that the linear acceleration is negative 7.656 meters per second squared. If we know one more piece of information, we can go ahead and figure out how long it takes to go from 50 radians per second down to, well, 10 meters per second. Those are two different types of quantities, right? So let us go ahead and find what is 50 radians per second in terms of meters per second. How fast is it initially going linearly? So again, we've got that v is equal to r omega. So v initial is equal to r omega initial, which gives us then 0.35 meters multiplied by 50 radians per second, giving us an initial speed of 50 times 0.35 is equal to 17.5. 17.5 what? That's right, meters per second. Radians vanishes, and we're left with the linear quantity. So this object was initially moving forward at a rate 17.5 meters per second, and we want to know how long does it take to drop down to 10 meters per second. We know three things. Velocities and the acceleration, we want to know the time. That's going to be really easy for us to get at this point, right? Correcto. So what do? We've got that v final is equal to at plus v initial, where the t is equal to v final minus v initial divided by a, which gives us, well, the final is 10 meters per second. The initial was 17.5 meters per second. And the angular, and the acceleration was negative 7.656 meters per second squared, which gives us the time being equal to, we got negative 7.5. 7.5 divided by 7.656. About 9.796, not 0.9796 seconds. So to go from 17.5 meters per second down to 10 meters per second takes just under a second. While to come all the way from 17.5 meters per second to rest is taking about 2.2857 seconds. That seems within the realms of feasibility, so we're good. All right. what else do we want? We want to know number of revolutions. How many times does this wheel spin around and going from 17.5 meters per second to 10 meters per second? How many times does it turn around? So now we're coming back to this right here. There's a couple different ways that we could do it, but again, I want an angular quantity. I'm just going to use angular quantities themselves. So, excuse me, we know the time that it takes is 0.9796 seconds to go from 17.5 meters per second down to 10 meters per second, which is 50 radians per second down to the corresponding angular velocity for 10 meters per second, which we don't even need because we've got this and we've got this and we've got this. We just want to know what delta theta is, so figure out what delta theta is. So put that down, and back over here, and we've got delta theta is going to be equal to 1/2 alpha t squared plus omega I times t. That's great. So delta theta is going to be equal to 1/2 negative 21.875 radians per second squared multiplied by the time of 0.9796 seconds quantity squared plus omega initial times time. Omega initial was 50 radians per second multiplied by 0.9796 seconds. So this will give us some delta theta, right? So let's go ahead and calculate what that delta theta ends up being. 5 times 21.875 times 0.9796 plus 50 times 0.9796. That looks all good. And I've got 38.496. 38.496. Great. 38.496. Is that the answer? It is not, because this is the number of radians that it sweeps through in its rotation. That is radians. We want the number of revolutions. We want number of revolutions as was asked for in the problem. So how are we going to get the number of revolutions? We got the number of radians, and we've got that 1 radian is equal to 1/2 pi revolutions. So 38.496 radians is equal to 38.496 divided by 2 pi revolutions. So we just take that, divide it by old friend 2 pi. Oops. Answer. And we get about 6.129. 6.129 revolutions. That's how many times it spins around and going from 17.5 to 10 meters per second. Pretty fancy, right? One last thing that we want, that we're asked for. We want to know how fast is this object moving after it spins around twice. So it starts at 50 radians per second, rotates 2 times. How fast is it going now? Well, equivalently, we have that it starts at 17.5 meters per second. It's going to spin around 2 times, and then we want to know how fast is it going now. So this stays the same because that's the constant of the system. That's not how fast it's going. Acceleration, okay, that's constant. And this is not the amount of time. Let's just deal with the linear stuff here, but we are told after 2 revolutions, how many radians is 2 revolutions? Excuse me, how many radians? What distance does 2 revolutions correspond to? Delta x. So first off, a couple different ways that we can do this. We'll do it step by step. we can convert that 2 revolutions into radians, right? 2 revolutions. Every revolution is 2 pi radians, so we've got ourselves 4 pi radians, and then we've got that delta x is equal to r delta theta, which is equal to 0.35 meters times 4 pi radians, giving us delta x, the distance that it moves forward in undergoing 2 full revolutions is 425 times 4 times a pi, 4.398, we'll say. 4.398, we just want to call it meters, radians phases out, so there's the distance that it moves forward, 4.398 meters, and now we want to know what? We want to know what's its final velocity. How fast is it moving after spinning around twice? Well, it better be less than 17.5, right? Because it's slowing down. So let's just go ahead and see. We know that after it rotates, a little bit over 6 revolutions, it's going 10 meters per second. So it better be more than 10 meters per second. Anyways, we just go ahead and compute this out, right? We want a final, we know an initial, we know delta x and a. Let's say that v final squared is equal to v initial squared plus 2a delta x. That's a nice one there because we don't know the time. So we can figure out what v final is. V final is equal to the square root of v initial, 17.5 meters per second, quantity squared plus 2 times negative 7.656 meters per second squared times the delta x, which we found to be 4.398 meters, and we get ourselves final answer for v final. Square root 17.5 squared plus 2 times 656 times that answer gives us 15.457. 15.457 meters per second. Spins around 2 times, moves forward a distance of 4.398 meters, and goes from 17.5 meters per second down to 15.475 meters per second. We can figure out the time interval for that. We can do anything. Anything regarding the object's angular or linear motion between this point in time and this point in time and or space, we can figure out. You just have to be able to navigate your way through these different angular quantities and linear quantities, make the connections between translation, and stick with the set. Read things carefully. Other than that, it's really just more of the same constant velocity stuff, constant acceleration stuff that we've dealt with quite extensively at this point. So that'll be that for now, and there's more coming with rotation. Lots to do with rotation. So until next time, take care.